Hi, I'm Dan Gelbart with an unusual collection of some devious shop tips. Let's start with the drill press, and the problem is, if you look here, ideally to drill a hole you need to use a center punch, make a punch mark, and then you want to use a center drill to deepen the hole, and then you follow it up with a regular drill. But there is a time-saving tip in which you can skip the center punch and the center drill. And to make it more difficult, I put this piece of metal at a slope, which makes it more difficult to start at the right location. So if I just start it normally, you'll see the drill is wandering. If you watch the tip of the drill, it's wandering because it doesn't have a center mark. But all what you need to do is peck a few times with the drill quickly. So after a few pecks, the drill doesn't wander at all, and you can drill through, saving a lot of time. Sometimes you need to tap a left-hand thread. Like if you can see, that's an M6 left-hand thread, but you don't have a left-hand tap. So an emergency left-hand tap is made by taking a right-hand tap and grinding it flat, so it leaves only a section in the middle, which is about a third of the tap diameter. And then for better tapping, you can grind in 2 grooves to give it a rake angle, to give the cutting edge a rake angle. So first you grind the tap completely flat, and then with a hand grinder you grind in 2 grooves. But this is still a right-hand tap. However, you can use it as a left-hand tap because the lengths are narrow, and I'll demonstrate. So you drill a hole first. You drill a hole first, and then you put the tap in, give it a bit of cutting fluid. Okay? And the trick, of course, now is to run the drill backwards, because you want to cut a left-hand tap. So instead of running it the usual way, I'm reversing the drill and running it backwards. And now you can see a hole with a left-hand thread, and I can prove it by threading in this left-hand threaded stud. So you can see I have a perfect left-hand thread cut with a right-hand tap. So here are 2 interesting lathe tips. So there are 2 types of self-centering chucks available for a lathe, a 3-jaw self-centering and a 4-jaw. A 4-jaw is much better because it can grip square stock, and it also distorts less because the gripping is spread over 4 jaws. But most people use a 3-jaw chuck because they think that they need it to grip hexagonal stock. But surprisingly, on a hexagon there are always 4 points which are equal distant from the center. So if you grip a hexagon in a 4-jaw chuck, it's completely free of runout, and I'll demonstrate. Okay, so if you look at the gripped piece, you'll see it runs through. To guarantee that it runs through, I can do a cleanup cut and then re-chuck it and show that it still runs through. So first let's do a cleanup cut. So now if I set up an electronic dial gauge, which reads out here, of course it will read 0 runout because I just machined it in place. So the proof is, if I take it out and rechuck it, if what I said is true about the 4 points around the center, I should be able to rechuck it with minimal runout. as you can see, there is a tiny bit of run out, and this is simply the repeat accuracy of the chuck itself. That's 100 micron per division, but these chucks only repeat to about 30 micron if you re-chuck. Okay, now another thing you can do in a lathe is to drill accurate cross holes. If you want to put a pin or anything, a thread, exactly on the center line of a cylinder, it's quite difficult to do without the right jig. The classic jig to do it is called a Regulus. It's a wonderful Swiss-made jig. The only problem with it, it's terribly expensive. The original Swiss one cost a few $1,000s. Now, however, there is a simple and cheap solution, is to replace the tailstock center with a V-block. So this is a hardened steel V-block where the V is exactly aligned with the center line. Now you can put the V horizontally or vertically, but it's more accurate to put it horizontally, because if you put it vertically, the tailstock may be misadjusted. In this case, it will be off-center. But vertically, you cannot change the position of a tailstock, so it's better to use it in this position. Now, if you put the piece you want to drill in the V will hold it exactly vertically on the center line. So if you take a center drill, you can drill it exactly on the center line. So here is a workbench trick that I'm sure most of you have seen, but it's so elegant that for the sake of the ones who haven't seen it, I'll repeat it. It's very common to have a bushing pressed into metal, like this is a bronze bushing pressed into a frame. But once these bushings are pressed in, it's very difficult to get them out because they don't have a through hole in order to retain the oil. So the elegant trick, if you want to replace such a bushing, is you fill it with oil and you hammer in a pin which matches the bushing, so the oil pressure acts like a hydraulic press and pushes the bushing out. So I put the pin in, and if I hammer it, it will push the bushing out. I'm just putting a rag over it just in case the oil splashes. So you can see the bushing lifts up, and you have to do it a couple of times because the volume of the hole is big. And one more time and the bushing will be out. The bushing comes out. Okay, so a related trick is sometimes you have two parts which are press fitted together, and it's very difficult to pull them apart. In this case are two different metals, bronze and aluminum. When you have two different metals, sometimes you can release a part by either heating or cooling. So if the bushing metal has a higher thermal expansion than the core, you release it by heating. If the bushing has a lower thermal expansion, you release it by cooling because the shaft inside will shrink more than the bushing. So in the case of bronze and aluminum, aluminum has a higher CTE than bronze, so the idea is to cool it. The problem is, in a normal shop, you can only cool it maybe in a deep freeze, so it's only like 30 degrees below room temperature, and that's not enough. So most people are tempted to put a stripper block, put it in a vise like this, and bang on it either directly or bang on it with some pin like this to get it out. But if it's a really tight press fit, it turns out that banging on it on this side is the wrong thing. Now the reason it's the wrong thing is that when you hammer on the inside, it becomes wider and grips even harder. And to illustrate that, the metal in a highly magnified way behaves like this piece of rubber. So if I take the piece of rubber and I compress it, it becomes wider because the material has to go somewhere. So if I hammer on it, each time the hammer hits it, it actually becomes wider. So it grips. On the other hand, if I can pull it, it becomes thinner. So there is by far more chance to pulling this bushing off by pulling the shaft instead of hammering on this side. And the way this is done, you take the same arrangement, put it in the vise, and you use a slide hammer. A slide hammer, I think everybody knows what it is. It's something used a lot in car work. You put a mess on the shaft, and you put something to prevent it from sliding off. So in this case, I'll put a nut. Now, if I move this back and forth fast, like a hammer, when it strikes here, it will stretch the rod. And if it stretches the rod, it becomes smaller diameter and it slides out of the bushing. So this way, with just a few blows, I can get it out of the bushing. While hammering on the other end could cause actually even mushrooming, which you'll never get it off again. So everyone knows that it's nearly impossible to spot weld aluminum on a conventional spot welder like this. There are some very specialized spot welders which have a very fast capacitive discharge, which could weld aluminum, but almost all spot welders in use are transformer-based, and they cannot spot weld aluminum simply because aluminum conducts heat too well. Same reason the electrodes don't weld to themselves. So if I take a piece of aluminum and try to spot weld it, okay, it looks like it's spot welded, but it comes off right away. So there is a trick how to spot weld aluminum, and interestingly, I learned this trick from one of the YouTube viewers of a previous video of mine where I explained spot welding, and the viewer told me that an old man once showed him how you can spot aluminum, and he wants to share the trick before it gets forgotten and lost. So the way you do it, you take 2 pieces of steel or stainless steel, and you sandwich the aluminum pieces between these 2 pieces. Stainless is a bit better than regular steel. So you put down a piece of stainless steel, you put down aluminum, you put down the second piece of aluminum you want to weld, and you cover it with another piece of stainless steel. So the aluminum is sandwiched between 2 pieces of stainless steel. And now you can weld. Do another weld. So, okay, so the stainless steel doesn't stick to the aluminum, but the aluminum is nicely welded, and if I bend it, you can see that it doesn't come off. See, I cannot get it off. Now the trick is, of course, the stainless steel gets hot enough to melt the aluminum. So it doesn't act like a normal spot welder. Just the stainless steel gets red hot and melts the aluminum into a little puddle. So that's indirect spot welding, but it actually works quite nicely. Now, a question I'm asked often is, how do you protect things from rust? Especially in a situation where they can be exposed to water, mist, moisture, and so on. So the absolutely best way to protect things from rust, of course, is to electroless nickel plate them, because electroless nickel plating not only protects from rust, but it's harder than any steel. It's about Rockwell 70, Rockwell C70, so it never wears off. For example, on this sander, which has water spray, both tables were electroless nickel coated 25 years ago, and in spite of the abrasive, the coating survived 25 years of continuous use. But sometimes the machine is too big, or you don't want to take it apart, so you don't want to send the parts for electroless nickel plating. So for example, I have this woodworking machine here, and I had no other place to locate it but next to a water jet cutter and next to this spray here. And some of the mist eventually will reach there. And as you can see, that 25 years later, there is no drop of rust here. So I want to explain a little bit the chemistry and how to protect from rust. So in order for things to rust, you have the two things, rust being a chemical action, two things produce rust. If you have an acidic pH, like in other words pH lower than 7, and if you have moisture. Now, even if your pH is not acidic, if you have moisture, it will rust, but rust slowly, like things in the rain will rust, although the rain is pH neutral, more or less. But if you have an alkaline pH, pH above 7, things will not rust even if there is moisture on them. The best example for that is those steel wool pads used in kitchens to scrub dishes, and you can see the steel wool pad is covered with some soap, and it can sit there for days and it doesn't rust, although it's always wet and it's steel wool, which is a lot of surface area, and one day the whole pad suddenly rusts. And this happens when all the soap is washed out, because the soap makes it alkaline. So as long as there is alkaline environment, meaning pH above 7, there is no rust. One day the soap disappears, and because steel wool has such a surface area, it all rusts in one day. So if you can keep the surface alkaline, which I'll explain how to do it, or if you can keep the humidity in the room below, say, 40%, things will never rust even if they are not oiled. Now, if you put oil on them, of course, it gives you protection. And the best oil to use is silicone oil and not regular oil or grease. And the reason for that regular oil or grease, which is hydrocarbon-based, washes off much faster, comes off much faster than silicone oil, which tenaciously sticks to the metal and creeps. So even area you didn't oil, the silicone oil will creep and enter every crack because it has a very strong wetting power. But in some situations, you don't want to oil. Say in woodworking machines, you really don't want to oil them because then all the wood dust will keep sticking to them. So if you can oil the machine, just use silicone oil regularly, and you don't really care about humidity or anything else. But if it's machinery you cannot oil, especially where dust is around, like woodworking machines, you have a few options. One option is to install a dehumidifier, make sure the humidity is always low in the room. Another option is to wipe the whole machine with a rag which has an alkaline material like NaOH. Okay? So if you take a rag and soak it in NaOH solution, and then you wipe the whole machine with it and let it dry, there will be like a fine white film formed on the machine, which doesn't collect dust and can be wiped off. But if the machine ever gets wet, the little bit of NaOH in the white film will combine with the water and form an alkaline solution on the machine, which will protect it from rust. So the way this woodworking machine is protected is basically by periodically wiping with a rag dipped in NaOH. Of course, you have to use gloves because the liquid NaOH is not so good for your skin. It doesn't have to be concentrated NaOH. It could be a mild solution, because any trace of NaOH, sodium hydroxide, any trace of that will make sure the surface is alkaline if it gets wet, and it wouldn't rust. Now, one other thing about rust, if you keep in the shop any bottle of acid, like nitric acid, hydrochloric acid, sulfuric acid, if you keep anywhere in the shop a bottle of acid, no matter how tightly it's closed, eventually everything in the shop will rust. And you can see that when you open a cabinet where acids were stored, no matter how much you taped the cap and everything, the inside of the cabinet is always rusty. because a plastic is not a hermetic seal. The glass bottle is a hermetic seal, but the caps today are made of plastic, and some molecules of the acid penetrate through the cap, and the slightest amount of acidic molecules in the air will bring the pH below 7 and things will start rusting. So you have to keep some acids in a shop for pickling and for other jobs, but don't keep them in the shop. Keep them in some storage outside the shop, because if a bottle like this ever spills on the floor, no matter how much you wipe it, everything in the shop will rust. Now, the same thing is true for materials which are not acid but can release chlorine, for example, bleach. Never be tempted to clean the floor in a shop with bleach. If you ever do that, you come back the next day, all the machines will be rusted. It happened to me once, so I'm talking from experience. So anything which can release chlorine or anything which is acid should never be used in a shop. And that's a very, very important thing. Same effect if you use a molten salt heat treatment, which is a very nice way of heat treating parts. Don't do it in the shop, because a molten salt bath releases chlorine as well. So if you stay away from acid and chlorine and follow these rules, 25 years later, you wouldn't see a trace of rust in your shop. Thank you.